Good morning, everyone. Welcome to AAAS and to today's conference. My name is Jessica Wyndham, and I direct the AAAS Scientific Responsibility, Human Rights and Law program. There may be some of you in the audience who aren't familiar with AAAS. We're 171 years old. I know we look good for our age. And we're the world's largest multidisciplinary scientific membership organization. We're the publisher of Science Magazine and the Science family of journals, which includes multiple journals, Science Robotics, Science Translational Medicine, Science Advances, which is an open access journal. And we're also home to multiple programs and centers, including the Scientific Responsibility, Human Rights and Law program, the Center for Public Engagement, and the Center for Scientific Evidence in Public Issues. This conference today is a partnership among AAAS, NIST, the National Institute of Standards and Technology, and the Innocence Project, in collaboration with the National Academy of Science, Engineering, and Medicine. So 10 years ago, the National Academies of Sciences published a report entitled Forensic Science in the United States, A Path Forward. The primary conclusion of that report was frankly quite shocking, that several of the forensic tools commonly used have little to no scientific basis. For decades, juries and judges were told that a fingerprint or tool mark found at a crime scene matched a known source to the exclusion of all others. Following the Academy's report and findings, these statements could now be challenged in courts. But it remained to be seen how courts would actually be affected by the Academy's conclusions, or how the scientific community would respond to the implicit challenge they set forth. This conference is being held to coincide with the 10th anniversary of that report. As you'll hear today, there's been a lot of activity in the subsequent years, and some of it's ongoing. Laboratories have adopted stricter practices, funding agencies have supported studies in forensic fields, and an understanding that human factors can affect the results of a forensic examination has become widely accepted. Among the efforts inspired by the National Academy's report were two in-depth analyses of AAAS. One addressed fire examination and the other latent fingerprint analysis. The reports generated a lot of attention, and just recently, very recently, Interpol said of the fingerprint report that it provided, quote, an excellent review of the subject and was, quote, a must-read. So with that, I'd like to turn to my colleague, Deborah Runkle. Deborah is a senior program associate at AAAS and manages the association's science and law activities, including those on forensics. Deborah will now introduce our keynote speaker. Thank you.
Good morning. Thank you all for coming. This event has been well anticipated, and we had a very good response. There are many people who are watching this on the webcast, which, by the way, will be archived after the meeting so that your colleagues who could not come will be able to see it. I'm here to introduce the first of our two keynote speakers today. The other will speak after lunch. Our speaker is, I'm going to give a brief introduction because you have bios in your program, so I don't want to take up a lot of time with introductions. The first of our two keynote speakers is Tom Albright. Tom is professor and Conrad T. Prebes Chair at the Salk Institute for Biological Studies. He's a member of the Human Factors Resource Committee of the NIST Organization of Scientific Area Committees for Forensic Science. Tom. 30 minutes.
Okay.
Questions.
I'll try. Thank you, Deborah, and good morning. I am deeply honored to be here to celebrate the 10th anniversary of this report from the National Academy. I should say at the outset that I was not involved in this report. I wish I could say that I was. I was at that time a basic scientist, as I am today, studying the brain bases of visual perception and memory. I think it would be fair to say that at the time the report came out, I was a forensic science hobbyist, in the sense that with a long-standing interest in visual perception and memory, I thought deeply about the kinds of problems that forensic scientists face on a routine basis. And I come to more or less the same conclusions that the National Academy's committee had done in this report. And that's what I want to talk to you about today as soon as my slides come up. I'm going to give you what I call a human information processing approach to forensic science, which really is a sort of summary of where we've come from and is a launching point for some new ideas about how to improve forensic science. So as I said, I'm going to talk about a human information processing approach to forensic science, and I'll begin with the following assertion, which is fairly obvious, and that is that, is this a laser pointer? I don't know if I have a pointer either. But the assertion is fairly obvious, which is that many forensic decisions are based on sensory information. And I'm talking here primarily about the so-called feature comparison methods. It is a pointer? Oh, excellent. Thank you. The so-called feature comparison methods, these are pattern matching problems that are common in forensic science, some of which are illustrated on the bottom half of the slide. And I'll begin with the following premise, which is that the root causes of forensic verity and error are tied to the operating characteristics of human observers, which is to say the sensitivity, storage capacity, and susceptibility to interference or bias. And I'll go on to say that these operating characteristics have been studied extensively by the basic science community for decades. There's nothing particularly unique about the types of feature comparison problems and pattern matching problems faced by forensic scientists, except perhaps the fact that the stakes are very high. We encounter these kinds of problems on a regular basis. Some examples are shown in the next slide. On the top half of the slide are things that are pattern matching problems that you solve on a regular basis. Finding your car in the parking lot, finding your luggage in the luggage carousel, despite the fact that many bags look alike. Finding the book you were reading on the bookshelf, or if you live where I do, finding your dog in a big pack of dogs at Dog Beach. On the bottom half of the slide are some more complex pattern matching problems that people face on a regular basis. And I want to stress that these are pattern matching problems that have been studied extensively by the basic science community, and that community has offered many suggestions for improvement of performance. The one on the lower left is the TSA problem, the problem of finding bad things in people's luggage. The one in the bottom center is a problem known infamously as sexing a chick. You may not be aware of it, but Americans eat something on the order of 25 million chickens a day, and we don't eat the roosters. And so there's a strong financial incentive on the part of the chicken producers to identify the gender of the animal at a very early stage of development. And the external genitalia of these animals at 2 or 3 days after hatching are almost indiscriminable. It can be done, and people can get good at it with some practice. And so a good chicken sexer can sex something on the order of hundreds of chickens, baby chicks per hour, which is what's necessary to keep up with the demand. And again, this is a problem for which the basic science community has contributed a lot of information. The case on the bottom right is the radiologist problem, the problem of finding cancerous tissue in the human body. And again, this is a case in which the basic science community has contributed a lot of information that has helped to improve performance. And so the product of this research, which is a principled mechanistic understanding of how perception and memory actually work, reveals ways to optimize human performance and avoid conditions in which people are likely to fail. And I could talk about this all day. I have a limited amount of time, so I'm going to focus on 3 factors that influence human performance under these kinds of conditions, with these kinds of tasks. And those are uncertainty, bias, and confidence. And to communicate what I mean by these terms, I have a little example, a little cartoon in the next couple of slides. This is a machine that I've invented. The machine has a sensor. That sensor is designed to detect that little green event in the external world up there. And when I plug the sensor in, the needle oscillates back and forth and eventually zeroes in on the value of that external event. And if I do this repeatedly, I get a series of measurements that vary around the mean, which hopefully is centered on the value of that external event. This is what's known as uncertainty of measurement. It comes about through the fact that the machine has some error in it, and the event of the real world may have some error associated with it. It's almost inevitable, and what we want to do is control it to some degree. In addition to uncertainty, we may also have bias. That is to say, we may get values that are on average lower than the actual value of the external event. This is the way your bathroom scale might work. Or you might get values that are higher than the external event. And finally, we have the phenomenon of confidence. In machine terms, what confidence means really is a compression of the dynamic range of the output such that the machine appears to be giving you a result that is more certain than is actually warranted by the measurement device. Now, if the machine were something like this, we could take it apart and identify the relevant components and identify what's causing these various sources of measurement error, uncertainty, and bias in particular, tweak it a little bit, put it back together, and perhaps reduce the error of measurement, get better performance out of the machine. But that's not the machine we're dealing with. This is the machine we're dealing with. And then the question is, what can we say about the performance of this machine? The human brain is manifestly an instrument of measurement. The field of neuroscience is a juggernaut of modern biomedical research and has chugged along over the past 50 years. And we know an enormous amount about how this object processes information. And one of the tools that's used for that purpose is this. This is what's variously known as either electrophysiology or neurophysiology. The point is that we can monitor the activity of individual cells or small groups of cells in the brain and look at how they communicate information, the types of information that are maintained by individual groups of cells. And from that, we've come a long way towards understanding how the brain acquires sensory information and processes that information such that we can make decisions. And on the bottom half of this slide is a cartoon that illustrates these various stages of processing. And I'm going to talk strictly about the visual system today, although the same principles apply to any other sensory modality. And let's suppose on the input side of things, we have two visual stimuli. We'll call them A and B. It doesn't matter what A and B are. They can be complex or not. The point is that they're different from one another. And at the earliest stages of processing in the brain, we have detection circuits. These are small groups of cells that are involved uniquely in the detection of either A or B. There's a circuit for A and a circuit for B. And if our task is to compare A and B, then ultimately we want the outputs of those to feed into this comparison circuit, which renders a quantitative output corresponding to the degree to which those stimuli are the same. And ultimately, what we want in this case is a categorical response. We want to classify things as either either same or different, a match or non-match. And in order to do that, we have to introduce a decision criterion, which is this bias term which is coming into play here, such that the classification stage renders an output that's either match or not match, or no match. And that's a statement about the properties of these two stimuli. So what I'm going to do in the next few slides is walk you through quickly these stages of processing, and then I'll use that as a jumping off point for some new ideas about how we might improve things based on that knowledge. So here's a detection stage. Again, we have a stimulus A. We have a neuronal response to stimulus A that's unique to that stimulus. We can represent that neuronal response as a pattern of activity in the brain in some high-dimensional space. This is necessarily true. And if we show a different stimulus, this is stimulus B, we get a different pattern of activity in this high-dimensional space. They may or may not overlap. It's hard to talk about high-dimensional spaces, so I'll just collapse these down for exposition to a single dimension, and that's what's shown here. This is the neuronal response to stimulus A. This is probability of the response on the y-axis. This is the magnitude of the response on the x-axis. And for different presentations of stimulus A, we might get different response magnitudes with a frequency corresponding to that probability. And that's what that blue curve is for stimulus A. And here's the corresponding curve for stimulus B. And in this task, ultimately, we want to compare A and B. And so we can conceptualize the comparison stage as really the joint probability distribution of these two detection responses here. And this is the simplest case, the case in which the two things being compared are the same stimulus. They're both stimulus B. Because we're talking about forensics, I'll call one of these the evidence and the other an exemplar. And the joint probability distribution is plotted in 2 dimensions in the center here, and the intensity of the red corresponds in the z-axis to the probability. And because this is circularly symmetric, we can project it onto the diagonal at the upper right. And this is what I call the noise distribution. I call it that because all the variation in this probability distribution has to do with error of measurement, because the stimuli are physically identical to one another. But we can look at a case in which the stimuli are different, and that's what's shown here. Now we're comparing B to A. That's the joint probability distribution. Again, projected onto the diagonal, we have what I'll call the noise plus the signal distribution, because this one actually has a signal owing to the fact that there's a difference in the inputs. And it's these distributions that we're really interested in here. And so I'm going to rotate this around 45 degrees and take a closer look. So again, we're plotting the probability of the response as a function of some measure of neuronal similarity. This is what's happening in your brain. And these are noise plus signal and noise. And if you follow what I've said so far, you'll realize that these correspond to different source stimuli, and that one corresponds to the same source stimuli. And this is a statement about ground truth. And I know it's a ground truth because I made up the problem. But what the forensic feature examiner has to work with is nothing more than this pattern of activity in his or her brain. And that's where the problem lies, because ultimately we want that person to render a categorical response. And there are 2 features of these distributions that are critical for that. One is discriminability, or D prime, that is the degree of overlap between the 2 distributions, which is affected by their relative means and their relative variances. And the other is the observer's criterion for making a decision about match or non-match. And if we set the criterion there, then all values of neuronal similarity that exceed that will be called a match. And this is actually a pretty good place to set the criterion, because we scoop up a lot of the same source stimuli and not too many of the different source stimuli. So this is a high accuracy position to set your criterion. But if we move the criterion down a little bit along this axis, now we're scooping up almost all of the same source stimuli and calling them matches, but there's actually now a much larger fraction of different source stimuli that are being called a match. And so the accuracy of this criterion is much lower relative to the original criterion I showed you. And this is really the problem. It's a problem that I'll call match promiscuity. The problem is there's not a unique relationship between a categorical decision of a match and the things that are happening in the observer's brain that underlie that match. And so 3 examples are shown here. This is what's known as an ill-posed problem. It's a problem without a unique solution. That is to say, there's an infinite number of possible conditions that could underlie a categorical decision of a match. And this is precisely the reason why validity testing, empirical validity testing, is so important, because we can't look under the hood and identify the conditions that gave rise to the match. All we can do is determine whether that match is actually accurate. And you can see that there are, in this set of conditions, this would lead to high accuracy matches. These 2 conditions would lead to relatively low accuracy matches. So that validity testing is critical here. But it would be nice if there were a means by which we could look under the hood and identify these underlying conditions. And you might suppose, since I told you that, before I go to that, let me point out that the conditions are actually more complicated than what I've drawn, because typically there are multiple exemplars, and so you have something like this. These are the similarity responses for each of the exemplars that are being considered, and that's the evidence from the crime scene. And the observer has to work with these internal signals in order to make a decision. And so you might suppose, given what I told you earlier about the way the brain works and the techniques that we have, that we could actually go in and actually record these underlying similarity responses. It's a nice idea. We're not there yet. We're not even close to being there, and I can't even envision a technical scenario in which we would be there. But we may be able to estimate, using some other techniques, these underlying neuronal similarity responses. And there's a technique that's been around for a long time for that purpose. It involves making confidence judgments. And the basic idea is that a forensic examiner can make a judgment about the confidence of an assertion of a match or non-match. And that confidence is in some way directly related to the similarity of the internal responses of that observer, reflecting the similarity of the exemplars to the evidence. The problem with confidence judgments, and this has been known for decades, is that they're very slippery. They're highly criterion dependent. They vary within observers. They vary across observers. It's just not a good way to go. But there may be another approach. Well, there is another approach. It's called perceptual scaling. And I'm going to tell you a little bit about perceptual scaling and some of the advantages that this has for estimating these underlying responses. This is where perceptual scaling comes from. It originates in the 19th century with this man, Gustav Fechner. Fechner invented what's called psychophysics. Psychophysics is the discipline that seeks to quantify precisely the relationship between the physical properties of stimuli in the external world and the internal responses of the observer, or in other words, to to identify the quantitative relationship between stimuli and mind. Now, about 50 years after Fechner, this man, Louis Thurstone, came on the scene. And Thurstone developed a very specific method for perceptual scaling, which I'll tell you about in a second. That method is based on some very cool mathematics that were developed by this man, Marquis Nicolas de Condorcet, who was the 18th century French mathematician who worked on voting theory. This was in the early days of democracy in France, and the goal was to try and find better ways for people to vote. But it turns out that the method that he developed is useful for this purpose. Now, perceptual scaling techniques have been around for a long time. They've been used in many different applied contexts, and probably the context that most of you are most familiar with is the following. This is what happens when you go to the optometrist. The goal of the optometrist is to correct your refractive error by putting lenses in front of your eyes, and what they typically do is put this great big apparatus in front of your head, and they flip out a bunch of lenses, and if you've been to the optometrist, you know the routine. The optometrist will say, which lens is clearer, number 1 or number 2? I think it was number 1 in that case. Which lens is clearer, number 1 or number 2? That was number 1. And through a series of these comparisons, basically what we're doing is this. Each one of these is a paired comparison, and upon presentation of each pair, the observer, the patient in that case, is simply voting for one member or the other. And the optometrist then does an analysis based on that, which has the following form. On the upper right-hand part of the slide are the pairs of stimuli that are being presented. Let's suppose there's 6 lenses here. They're referred to as images, but let's suppose they're just lenses in front of your eyes. There's 6 of them, and you vote upon each presentation for one or the other. You're making a relative judgment. Those votes are tabulated in the matrix at the upper left, and they're summed down each column to give us a total number of votes for each lens. And then we normalize them relative to the total number of presentations of each pair. That's what's plotted on the lower left. This is voting score as a function of lens number. And we can order these as a function of that voting score as we've done on the lower right. So they're rank ordered there. And if you do this enough times, you can get a measure of error variance associated with each of these things. And if you followed this, you'll realize that at this point, what we have are estimates of the underlying similarity responses elicited by each one of the lenses relative to the goal of perfect refractive correction. And so this is a very cool technique. It's, like I said, it's been around for a long time, and it has lots of potential for application in the forensic sciences. We wanted to try this out. And for technical reasons, we chose the problem of eyewitness identification to test this. It's just easier for a variety of reasons I'll come back to in a few minutes. Also, I got involved in eyewitness identification as a result of my participation in this committee, which I chaired with Judge Jed Rakoff. I fell down the rabbit hole of all things eyewitness a few years ago, and I'm still there, apparently. And so if you follow the eyewitness identification literature, you'll know that there are 2 standard techniques that are used commonly. They're for lineups. There's so-called simultaneous lineup, in which all the faces are presented at the same time, and sequential, in which they're presented one at a time. And there has been extensive discussion about the relative merits of these 2 techniques. I'm not going to talk about that at all. I'm going to tell you about a new technique that we invented, which is based on the method of paired comparison, which has the following form, which you'll see is similar to what I described for the optometrist. There's 6 faces in the lineup. We present 2 faces at a time, and the witness simply votes for one face or the other. The task they're given is to say, which of these two faces looks more similar to the person you remember from the crime scene? It's a forced choice task. They have to answer on every presentation. And they're making relative judgments. At no point do they make an absolute judgment about who the culprit is. And these are data that we get from that task. These are data that are averaged across 65 subjects. And so this is voting score and as a function of face number. These subjects saw on the day before a mock crime, and the person who was in the culprit in the crime is face number 1. And it turns out the face number 1 naturally bubbles to the top here. But the great thing about this is that we get all this information about what's going on under the surface, which you can't possibly get given any standard lineup procedure. And that puts us in a position to determine the likelihood of confusing each of these stimuli with the stimulus with the target stimulus, the culprit. And so once again, we have, by this method, estimated the underlying recognition memory responses in the eyewitness's brain by applying this technique. And this puts us in a position in which we can apply a statistical technique. It's a process of statistical inference. It's basically the application of a binary classifier to these data such that we can, in a criterion independent way, determine the likelihood that an ideal observer looking at these data will classify the outcome as either identification of the culprit or misidentification of an innocent suspect. This is what's known as ideal observer analysis commonly in this literature. And the result is presented in the form of a receiver operating characteristic curve. You don't need to worry about too many of the details here. The point is simply that the y-axis is the hit rate or correct identification rate. The x-axis is the false alarm rate or false identification of an innocent suspect. And the ROC curve that we get is indicated by this solid line here. Gray is the 50% confidence interval, and dashed lines are 95% confidence interval. And this is actually really good discriminability of the culprit relative to an innocent suspect. And we wanted to compare this to existing methods. So we took some data from the literature. These are data from John Wickstead's laboratory, which we plotted on top of our data. And you can see that our method compares quite favorably to that, with the addition that we get the entire ROC curve. So we're ultimately getting a much more precise estimate of the witness's ability to discriminate the culprit versus an innocent suspect. But really the power in this method lies in the fact that you can apply it to individual observers. These are data, you can't possibly do this with any other method that's out there today. These are data from 3 witnesses that were part of our experiment. The witness on the left here did extremely well. The one in the middle did moderately well. This witness over here is pretty much useless. And we can quantify that. We can quantify that by what's called the area under the curve. This is a standard metric for looking at ROC curves. Again, the y-axis is hit rate, the x-axis is false alarm rate. And this area under the curve is 0.85, and you can see that they decline as you go to the right. And this, again, is a precise quantitative estimate of the underlying certainty of the witness's response, which, as you might imagine, would be of enormous value, as an enormous probative value to the trier of fact. And so we consider this a success, and we're trying to, our next step is to do a field study with this and try to get it accepted by people who actually perform these procedures on a regular basis. But that led us to question whether you can actually take these methods and apply them to other forensic procedures, other feature comparison methods. As I mentioned, there are technical reasons why the eyewitness case is simpler to do, mainly having to do with the fact that eyewitnesses are just ordinary people, so you can just get ordinary subjects, ordinary people as subjects, whereas forensic feature comparison tasks are performed by experts who are trained specifically. And so there's a logistical problem associated with gathering the subjects, but it can be done. And you might imagine if you were going to test the validity of bite marks, you could set up a program like this in which you present a series of bite marks, denture pairs, and ask which is more similar to that at the crime scene and get at the underlying processes that give rise to a decision about match or non-match. Now, everything I've spoken about thus far has to do with the operating characteristics of individual observers, and I just want to take a couple minutes at the end to speak about the operating characteristics of the group, because this is an important direction in forensic science, and I'll introduce that by going back to Nicolas de Condorcet, the 18th century French mathematician. Condorcet is most well known for something that's referred to as Condorcet's jury theorem. This is a well-known theorem. It follows naturally from the law of large numbers. And the theorem goes as follows. If each member of a group is faced with the same binary choice, and you can see the relevance to forensic science there, and each member of the group is independently capable of making that choice correctly with a probability of at least 50%, then the probability that the majority decision is correct will exceed that of any single member. That's point number one. And point number two is the probability that the majority decision is correct will approach 1 asymptotically as the number of members of the group increases. And we can display that graphically as shown here. This is the accuracy of the majority decision is on the y-axis. This is the group size, the number of examiners on the x-axis. And again, this is a well-known theorem, and it is in fact one of the reasons why in forensic science decisions are typically made by more than one person. And the explanation for why this happens, again, it follows from the law of large numbers, but the explanation is illustrated here in cartoon format. Let's suppose we have a number of examiners, and these examiners vary in terms of their sensitivity and their biases that they bring to the table. All of that is error variance. And when we sum up their responses, the error variance washes out so that the majority decision is more accurate than the behavior of any individual. But if you think about this and its application of forensic science, you realize that there's a resource problem, which is that it takes a large number of people working on the same casework in order to get a highly accurate response. And although you could argue, well, that's a premium, we really want a highly accurate response, we may not have the resources to do that. And so the question then is, can we kind of amp up this and approach 1 more quickly with a small number of people in the group? And there's some ideas about this that come from the concept in biology known as quorum sensing. Quorum sensing comes from study of bacteria, and I'm not going to talk about the bacteria. The point is simply that individuals in a population, a high-density population, will behave often differently than the way they will behave alone. And there are lots of examples of this kind of thing in biology, herd behavior and flocking behavior. And so can we exploit this somehow in order to improve group decision making? And this has actually been done in the medical field, the field of medical diagnosis. This is a paper published just a couple of years ago looking at collective intelligence. And the basic idea is the following. That is, you have a range of performance by the examiners. In this case, it's radiologists, but in the case of forensic science, it would be the forensic examiners. And we look at that range, and we identify the poorest performers and the best performers, and we find a threshold that's somewhere in the middle of that, which we call the quorum threshold. And the next step involves simply identifying, and that's determined based on casework that's similar to a particular casework, so we just have a general sense of their performance. And that information establishes the quorum threshold. And then on the casework at hand, we identify those performers who are better than the quorum threshold, and they get a yes vote. Those who are worse than the quorum threshold get a no vote. And the end result is that you actually get a decision that approaches 1 at a faster rate than you do with the majority rule, the Condorcet rule, jury rule. So there's, again, enormous potential for this. This is the data from the radiology radiology study that I was just referring to. I don't want to go into this in any great detail, but accuracy is plotted on the y-axis, group size on the x-axis. The red dots are the majority decision, and the black dots are the quorum decision. And you can see, again, the red is the Condorcet rule. The black dots are the quorum decision, and you can see that performance improves and approaches high values at a faster rate than you do with the Condorcet rule. Now, we tried to apply this to the eyewitness data that we have for a whole variety of reasons. This is not really a legitimate comparison, but it's an exercise to demonstrate feasibility. And what I have in the next slide is an illustration. This is just fresh off the press. We just did this. But the point is that you can increase the area under the curve, which is a measure of discriminability, by significantly by increasing the number of subjects that are involved. Now, the problem with eyewitness identification is you don't have, the number of subjects is not a tractable variable. It is what it is, and so you can't really do this in practice. You could do this in other types of forensic feature comparisons, and as a result, we get much better. This is with a large number of subjects, and this is with a small number of subjects, and you can see how performance improves significantly as you increase the group size. And I just want to close with this is a quote from Jennifer Mnookin, which many of you know for her work on forensic science reform, which I'll read to you. Evaluation of a forensic technique should be more concerned with whether the technique has been adequately validated by empirical testing than with whether the expert can offer adequate description of the theory from which the claims derive. I completely agree with this, but I've spent the last 30 minutes giving you a description of the theory from which the claims derive. And so you might wonder, well, what gives with that? And the answer is that it is generally true in science that mechanistic understanding of a process will suggest novel techniques for measurement of some quantity associated with that process. Or to put it differently, if we lift up the hood and look at the mechanism inside, we're in a much better position to identify points of measurement that will give us a better reading than we would if we simply do a black box study and look at the relationship between the input and the output. And I will close with that, and thank you very much. Okay.
Any questions?
Question? Yeah.
The study where you showed the 3 sets of paired observations of witnesses based on the method of paired comparison, how many entries for each one? Was it like 36, 6 times 6?
So for each pair, so I showed you a couple of things. I showed you data from the population of subjects. Each subject was shown each pair 3 times. There are 15. If there's 6 faces in the set, there are 15 possible pairs, and each pair was shown 3 times. So we get a rough estimate of error variance from that. But then we looked at the population. Mainly we looked at the population because that's the only way we can compare our data to the existing techniques, because they're all population-based. We can do this individual-based analysis as well. Did that answer your question?
One more question back there. So in your study of the impact of adding additional observers, did you look at whether or not it matters, and if so, what the significant, how much it matters, whether the observers know what the prior observer picked? So did you replicate the verification process that's typical in forensic cases where the verifier knows the opinion of the original examiner?
That's a good question, and it points out that I went over that very quickly. The method is slightly complicated. What you actually do is establish the performance of a group of people on a particular type of forensic, in this case, well, that was radiology, so a particular type of radiology exam. So you know generally what their performance level is, and then you establish the quorum threshold based on that, which is somewhere in between the best performers and the worst performers, and then you give them another task, look at their performance, and then look to see whether the threshold they use for performing in that task exceeds the quorum or doesn't exceed the quorum. All this is done at a sort of meta level. That is, there's somebody looking at the behavior of the people in the original test and then the final test and putting them into these categories of good performers and bad performers, and then coming up with a quorum decision. I don't know if that really clarified it very much.
Join me in thanking Dr. Albright.
Thank you.